Okay, awesome. So after such great news, my talk will sound much better. So that's nice. Yeah, it's really great to be back first. Really excited to be here. And this time I'm going to be talking about something different than what I talked about last time, which is, first of all, some work I started as a grad student at the University of Washington a few years ago. And then now I'm kind of putting together as a postdoc at Perimeter Institute. And also now working in collaboration with my friends and collaborators here. But the idea is just to modify how massive neutrinos are implemented in Boltzmann solvers. And I'm going to explain exactly what it is in a second. But just some basic motivation. Of course, we're all here because we have a common goal of learning fundamental physics from our cosmological surveys, from galaxy surveys. And this audience is also very familiarized with the simple fact that learning about fundamental physics from galaxy surveys always requires scanning and computing cosmological observables or scanning over a very high dimensional parameter space, which is a computationally expensive enterprise. And specifically, of course, the backbone of any basic computation in cosmology is linear perturbation theory, right? We always have to do linear perturbations before thinking of anything else. And if you want to turn on massive neutrinos, this is actually really annoying and computationally expensive. So for example, a code like class does a lot of computations. It has to include lots of species together in this coupled system of equations. But as soon as you turn on massive neutrinos, you find that the code takes twice as long to run. And so the goal here is to try to find something that's more efficient than what currently exists. Good. So first, let me just remind you what's the culprit here. So why is it that neutrinos slow things down significantly? And that's just because there's velocity dispersion. So not all the neutrinos are traveling at the same speeds. Once they become non-relativistic, some are faster than others. There's a whole distribution in velocity space. And what that means in practice is that you no longer can get away with writing some fluid equations. You actually have to go ahead to full phase space and solve the Boltzmann equation, keep track of different momenta and so on. And that's a slow procedure. Good. But at the end of the day, so we have to solve equations in phase space. But at the end of the day, we don't actually care about phase space in a way. We only care about integrated quantities. So we go ahead, we write a multiple expansion for the distribution function in terms of the angles between the wave number and the momenta. And you can go ahead and write, I don't know if this points or what, doesn't matter. You can go ahead and write this integrated quantities is just like the things that you actually care about, that integrals of these multiples times the energy of the particle times velocity to the power of the multiple. And just to exemplify, so if you set L equals 0, just get the density, velocity, shear stress, and so on. Those are the things you care about because those are the things that actually couple to the Einstein's equations. And that's also kind of like what makes this slow and expensive. It's just that you have to do, at each time step that you're running something like class, you have to do a bunch of momentum integrals because you have to evaluate the neutrino dynamics. You have to integrate over phase space to get these fluid quantities and feed that back into the Einstein equations. So that kind of like makes things much more expensive. Good. So there is this is how to solve the further fluid dynamics, but there's also a very important tool that's integral part of class, for example, is fluid approximations. And the way how this usually goes, you're all familiar with the fact that fluid approximation is just mass conservation and momentum balance. But in order to write down a fluid equation, for example, for a massive neutrino species, you need to specify some ingredients. So things like what's the sound speed, what's the shear stress. The standard approach for what you say for the sound speed is you say that's a scale-independent thing. For class, for example, when the fluid approximation is used, we just say it's an adiabatic sound speed, so something that's just a function of time. Of course, it just goes like 1/√3 of the speed of light early on, it's relativistic, and then goes to 0 as it becomes non-relativistic. But say position independence and size that you make for the sound speed. So kind of like for now, I have explained to you the basic ingredients, everything that goes into the standard implementation. So now let me tell you about some ideas and things I've introduced in the past and that I'm now combining. So first is like a different route for solving the complete dynamics. I call this the generalized Boltzmann hierarchy. And the point is that now you're going to do, besides having the multiple expansion, that's the standard. Yeah, I now just want you to introduce consider like also adding some velocity weights to this moment expansion. And the whole point is that once you, in terms of those quantities, you get equations of motion for this FLNs. It's a completely closed system of equations. You integrate out phase space completely. So you arrive at some. I don't really specifically care too much about the specific structure of the equations, but these FLNs couple to each other. So L coupled to L minus 1, L plus 1, the N coupled to N plus 1, N minus 1. But it's a closed system of equations where you don't have to do integrals or momentum. So that's the basic idea. So right, the main features of this is that there's a very clear physical interpretation. So this higher N weights that you're adding is just really probing faster moving particles. Of course, in order to make this, to turn this into a system of equations you can actually solve, you need to truncate. So I need to be able to tell you how to truncate at some point and to have a finite system of equations, but that's something that we can figure out. And very importantly, there's no momentum integrals whatsoever. So for example, if you want, you can go ahead to Mathematica, write ND solve, and it solves it. It's really simple. Right. And another tool that I'm combining with this generalized Boltzmann hierarchy is this dispersive fluid approximation. So the idea here is that we always make these ansatz. As I told you, that the fluid approximation is just position independent, scale independent. But if you just go ahead and compute it, you're going to find out that, right, on the very largest scales, it does just track this adiabatic sound speed, this adiabatic ansatz. But as you increase the value of k, it just deviates from the adiabatic and actually approaches something else, which I'm calling the asymptotic in this curve. So the behavior of the sound speed is just adiabatic on large scales, but then asymptotes to some analytic formula that can be easily computed on small scales. And the claim is that once you take that into account, when you account for the dispersive nature of this fluid, the fluid approximation works much, much better. Right, and then what we did now is to actually put this all together in the Boltzmann solver. So actually implement this on class. And I just wanted to show you, for example, predictions for relevant meta power spectrum, the neutrino power spectrum, and the cross power spectrum. The black curve here is some reference kind of like high precision setting evaluation of class where you set the maximum multiple to be quite high. And the red dotted curve, NCDM, is kind of like what if you just run class in default precision settings. That's what it looks like. And our implementation is GBH in blue. On the left is just like the power spectra themselves, and on the right is relative errors compared to the reference. And I'm also including on the right like how much time it takes to evaluate each one of those different settings. And the point is that our implementation of GBH is more accurate than what class is currently doing. So you can see, for example, if you want to get neutrino transfer functions to be accurate at late times, like up to a 10% error max, then just the default precision settings on class won't do, but the GBH does, and it's also faster. So right, and now we're final stages of putting this together and making this available. But right, so the key takeaways, I have no idea how much time I have left, but the base idea here is that I introduced this generalized Boltzmann hierarchy, which just allows you to effectively integrate down the momentum dependence, and the resulting system of equations is just much simpler and faster than traditional methods for how doing this. Second is that the fluid approximation is much more accurate when you just account for the dispersive nature of the fluid. And so the main important takeaway that I want you to keep is that this coupled system of GBH and dispersive FA is both more accurate and more efficient than the standard methods. And for now, I'm just considering the scenario of standard neutrinos, but for the future, I think this is also just a very simple and flexible framework for like considering a general NCDM species with non-standard properties. So yeah, and stay tuned for that. I hope to go in this direction moving forward. Thank you. Right. Right. Correct. No, I mean, we solved a couple system of equations as is, so we take into account the fact that there's, right, it's mostly diagonal. Right. Oh, right. I mean, I don't solve maybe let's talk about this. This sounds interesting, but so far I really just like write the line of equations and solve naively. Maybe right. There's some optimizations that I want to do actually. So this is like kind of like the first where I showed this for the first implementation. But I think there's a lot of obvious things that we can do to make this even faster, and I think we'll be able to reach actually better results. But yeah, let's talk later. Then we maybe have some ideas. Right. 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 No. It's these big errors are all in the fluid approximation. So just the fact that on short scales the sound speed is not really adiabatic. It asymptotes to the other synthetic formula. You can not use the fluid approximation, but that's going to be like 3 times as low to run. So that's why in standard precision setup, you just run the fluid approximation. And what I'm telling you is that you can still use the fluid approximation and get very accurate results. Just have to properly modify it to account for this dispersion. Yeah. Right, ref here is like solving the hierarchy with like L max equals 40 or something. Right, it goes to go how to high. Right, the obvious thing should do nothing. Yes. Right. Thank you.